In certain parts of Australia, Africa, and even the American Southwest, that subtle shimmer isn't just mineral sparkle. It's a sign that something much heavier and far more valuable has been pulled from deep underground by tireless foragers with 6 legs. Ants and termites don't just disrupt the topsoil, they inadvertently sample the substrata, drawing trace elements, including fine gold, to the surface as they excavate. The trail doesn't lead to food. It leads to data, and sometimes to gold. The phenomenon isn't new, but its implications are still underutilized. Ant and termite mounds have long been a curiosity in arid landscapes, symmetrical, persistent, sometimes sprawling meters across. Yet researchers and prospectors have found that these insects can be hyperlocal geochemical samplers. As they tunnel, they bring up grains from as deep as 10 meters, often across strata that remain inaccessible without drilling. That means, in regions with deep alluvium or transported overburden, insect mounds provide a rare, passive window into what's hidden below. What catches the trained eye first isn't the gold itself. It's the anomaly in luster and weight. Under the right light, some mounds show a peppering of metallic flecks. Most of the time, it's iron oxide or mica. But occasionally, these specks are unusually dense and refuse to float or smear. They're inert in weak acid and survive repeated washings. This is where visual intuition gives way to field tests, and where a missed opportunity can become the start of a new grid. In one documented case in Western Australia, systematic sampling of termite mounds over a flat, featureless expanse led to the discovery of a buried gold deposit with no surface expression. The mounds had concentrated gold fines in the sub-10 micron range, far below visual detection, yet enough to register with fire assay and ICP-MS analysis. The key was pattern density. When mapped, the gold-positive mounds formed a rough linear trend that aligned with a buried quartz reef identified later through drilling. That discovery reframed the way insect mound geochemistry is understood, not as a novelty, but as a low-cost, low-impact reconnaissance tool. While it's not definitive on its own, it's a way to dramatically narrow down a wide area before committing to more invasive or expensive surveys. And for independent prospectors without the budget for aerial magnetics or soil drilling, it's one of the few tools that trade sweat for signal. But if you're standing there, staring at a mound glittering in the sun, the next move isn't to dig. It's to sample, cleanly, repeatably, and with discipline. Because not every mound that sparkles points to gold, and the line between a lucky find and a false lead is thinner than a hair. So how do you tell which signals count? Most gold-bearing mounds don't look any different from ordinary insect nests. No dramatic color change, no obvious quartz float. The trap lies in the subtlety. Instead of a glowing beacon, the first real signal is often a slight variation in luster or grain weight that only becomes obvious under close inspection. What separates a routine mound from a potentially gold-rich one isn't size or shape. It's texture, mineral distribution, and in rare cases, a fine film of metallic residue that won't wash away in the wind. Begin by examining the soil texture on and around the mound. Gold-bearing soils often include unusually fine, heavy grains concentrated toward the center. Even before tests, a mound that feels heavier when scooped, dry weight versus apparent volume, can indicate the presence of higher density minerals. This weight-in-hand test is crude, but often surprisingly predictive, especially when compared across multiple mounds within the same terrain. Next comes visual scanning under angled sunlight. Train your eye to spot specular reflections. True gold doesn't twinkle or flash. It glows steadily, even in diffuse light. Pyrite will sparkle and flake under pressure. Mica shimmers in sheets and feels greasy to the touch. But gold, especially in microparticle form, clings to the surrounding material with a quiet density. Under magnification, 10x loop or clip-on macro lens, You may see flattened specks nestled in iron-stained fines or sulfide clusters. The surrounding vegetation can also provide subtle clues. Plants growing atop or adjacent to gold-positive mounds sometimes exhibit mineral stress, stunted growth, chlorosis, or even altered root structure in hyperaccumulating species. These secondary signals aren't reliable on their own, but, when paired with mound characteristics, help build a case. Importantly, not all ant or termite species are equally useful. Harvester ants in desert regions and specific termite genera in tropical belts tend to excavate from deeper strata than surface foraging species. Their nest architecture also matters. Large, dome-shaped mounds with clear central chimneys often tap deeper horizons than flat or sprawling nests. If your sample sites include both types, prioritize the domed or columnar forms first. A useful field trick involves isolating a single mound and creating a control. Take a 250 milliliter sample directly from the center and another from the surrounding undisturbed soil at the same depth. Then compare the weight after drying. Even a 5 to 10% increase in post-sieve residue from the mound sample may warrant further testing. And if visible gold specks persist after sieving and magnet sweeping, you're past the point of speculation. You're into validation. But how far do these signals extend? One mound with a few gold particles might just be an anomaly. A line of mounds, spaced along a subtle gradient and showing consistent trace recovery, suggests a structural control below. Possibly a shear zone, a quartz vein, or a disseminated deposit. Connecting those dots requires not just observation, but a pattern. And to start that pattern, you need to know what terrain supports these clues in the first place. Insects aren't prospectors, but their behavior can mimic one. Over years and decades, certain species of ants and termites build and maintain nests that span vertical soil profiles. In doing so, they bring subsoil particles to the surface with extraordinary precision, grain by grain. And if those deeper layers contain gold, however fine or locked in, the insects act as tiny, tireless samplers. The result isn't random. It's a geochemical echo of what lies beneath, compressed into a mound that fits in the palm of your hand. Termites are particularly effective. In tropical and subtropical environments, mound-building termites excavate material from multiple meters below the surface, often down to the bedrock interface. These particles are incorporated into the construction of their hard, cemented mounds, making them geologically stable and temporally reliable. Unlike surface soils that are subject to wind and water erosion, these structures can preserve trace elements from buried mineralization zones for decades. Ants, especially harvester ants and red mound ants common in arid and semi-arid regions, offer similar sampling utility. Their nests are often less cohesive than termite mounds, but their tunneling behavior extends deep into the regolith. During excavation, they discard unwanted material around the mound perimeter, often forming concentric rings of excavated finds. These discarded particles may contain gold-bearing minerals in trace but detectable amounts. Several academic studies and industry surveys confirm the relationship between insect mound chemistry and underlying mineralization. For instance, in Western Africa, termite mound samples have led to the discovery of previously unknown greenstone-hosted gold systems. Likewise, in parts of Western Australia, ant mound analysis has identified gold anomalies where traditional soil sampling failed due to deep transported cover. This is possible because gold, even in ultra-fine form, can adsorb onto iron oxides or be locked within sulfides, both of which are commonly mobilized by insect activity. Mound materials often concentrate these denser particles due to the insect's preference for finer-grained, clay-rich soils when building and maintaining structures. The result: selective enrichment of indicator materials at the surface. But the value isn't just in the presence of gold. Mounds can also reveal pathfinder elements: arsenic, bismuth, antimony, and mercury, depending on the host geology. These can act as red flags for hidden systems, even when visible gold is absent. By targeting mounds with elevated multi-element anomalies, prospectors can focus follow-up efforts on the most promising zones, conserving time, budget, and access rights. However, insect geochemistry isn't universally applicable. In recently disturbed terrains, such as plowed farmland or reclaimed mine sites, the geochemical integrity of mounds may be compromised. Similarly, in regions with shallow groundwater or highly leached soils, the signal may be too diffuse or chemically altered to trace. The best targets are undisturbed, well-developed mounds on stable surfaces with minimal sediment cover. To leverage this behavior, prospectors must not only find these mounds, but track them. That means mapping their positions, assessing their architecture, and sampling in a repeatable manner. Because if one mound holds a clue, a dozen might define a structure. But to begin drawing those lines, you'll need a grid and a method for translating insect scatter into subsurface logic. What looks like random scatter from a distance can reveal structured subsurface truth when plotted with precision. The key lies in transforming insect mound locations, each a passive sampler of what's below, into a spatial dataset. While many prospectors still rely on instinct or proximity to outcrops, systematic mapping of ant or termite mounds allows for predictive targeting, even in terrain with no visible rock or mineralization. Done right, it turns a chaotic field into a geochemical radar. Start with a grid. Even a basic 100 by 100 meter overlay using GPS waypoints can transform how data from mound samples is interpreted. Each mound becomes a node, and each sample, labeled, recorded, and logged, feeds into a broader pattern. When gold-positive samples begin to cluster, they often reveal alignments that are anything but random. Mineralized veins, shears, or intrusive contacts that channel gold deposition. Some of the strongest case studies in this approach come from regions where traditional soil sampling is unreliable. In central Burkina Faso, termite mounds were found to align in a northeast trending corridor overlying a buried gold system. The termites had tapped into mineralized saprolite zones and concentrated gold particles in their mound caps. When these mound locations were plotted, they matched both the structural controls and magnetic lineaments visible only in airborne data. For independent fieldwork, the process requires discipline. GPS marking for every sampled mound is non-negotiable, even when walking blind across plains. Note the species, mound size, structural type, dome, column, flat, and any visible surface features like iron staining, salt crusts, or quartz float. Photograph each sample site with a scale and compass bearing for later reference. These details, though mundane, become critical when patterns emerge, especially if you're dealing with micrograin anomalies that don't show up to the naked eye. It's also essential to maintain sample spacing that balances resolution with feasibility. In reconnaissance stages, 200-meter spacing between sample points may be enough to detect trends. In infill phases, after a cluster is identified, spacing can tighten to 50 meters or less to resolve structural edges. Some use drone imagery or LiDAR overlays to accelerate mapping, but even without these tools, a handheld GPS, notebook, and consistent walk pattern can produce professional-grade results. The real payoff comes when spatial analysis overlays geochemical results. A string of low-level gold anomalies across mounds may seem underwhelming in isolation. Say, 0.02 to 0.05 grams per ton gold in pan concentrates. But if that string lines up with a mapped fault or coincides with arsenic or iron oxide enrichment, it shifts from curiosity to vector. And if several adjacent mounds all test positive above background, the odds of buried mineralization increase sharply. However, to avoid chasing noise, the mapper must filter for context. Isolated hits outside known structural controls are often false positives, especially in terrains with erratic insect behavior. Likewise, avoid over-interpreting results from clustered mounds. Ants and termites are social, and their nests may reflect proximity more than geochemistry. Only consistent, multi-point anomalies across space and species suggest a real subsurface driver. Once your grid is in place and promising trends begin to form, the next logical step isn't drilling, it's sampling. Not deeper, but more targeted. The mounds have shown you where. Now you need to extract enough from each to test what. And that starts with learning how to collect without contamination and how to separate signal from silt. The temptation is to dig deep and hard, but the smartest first move in insect-driven prospecting is light and fast. A controlled sampling pass, focused on collection, not excavation, yields more actionable data with less disturbance. Each mound becomes a probe, and the goal is to harvest just enough of its geochemical record to confirm or dismiss its relevance. Done right, a single operator can cover over 20 sample points in a day, especially in dry conditions where transport and sieving are efficient. Start by selecting the target zone, central mound cap, perimeter fines, or both. The cap, especially in termites, is cemented and can contain subsoil particles used for structural strength. In ants, the loose soil near the central entry often contains the freshest material from depth. Use a clean, non-metallic scoop or trowel to remove roughly 200 to 300 grams of surface material from a consistent location on each mound. Avoid material with vegetation, moisture, or organic crusting, as these can skew test results. Each sample must go into a pre-labeled Ziploc or sample bag with its GPS coordinates, mound type, and sample location, e.g., top cap, east base. If weight allows, carry a field balance to verify sample uniformity and ensure enough material remains for sieving and pan work. Dry samples are essential. If moisture is present, air dry them in shade before bagging to prevent clumping or microbial alteration. The goal in this initial pass isn't visual confirmation of gold, but an indicator sweet. Heavy minerals, dark fines, and any metallic glint that persists after sieving. Back in camp or at a field station, dry sieve each sample through number 20, 0.85 millimeters, and number 40, 0.425 millimeters. Mesh to separate coarse material from fine heavies. Concentrate the -40 fraction. It's here that gold fines, iron oxides, and pathfinder elements typically accumulate. The concentrate is then ready for quick field tests. A simple black plastic gold pan or battue, combined with a magnet sweep, can reveal surprising details. Start with a dry magnet pass across the fines to remove magnetite and ilmenite. Note the volume removed and its grain size. Then wet pan the residue gently, allowing heavies to settle and lighter silicates to float away. In good samples, you'll see yellow or bronze flecks that remain in the corner, too small to grab, but too dense to wash away. This is where judgment comes into play. A mound sample with even a few gold-colored grains that survive panning, magnet pass, and acid rinse, more on that later, deserves follow-up. But equally important are samples with no visible gold, but heavy sulfide concentrations, strong magnetic residue, or elevated black fines. These may reflect deeper mineral systems where gold is locked in pyrite or arsenopyrite. Not visible in the pan, but assay positive later. Field notes at this stage are your most valuable tool. Record not just what was found, but how each sample behaved. Did it smell sulfurous when wet? Did any particles float unexpectedly? Were there bubble trails, color changes, or persistent films after panning? These small signs often correlate with gold even when it's not visible. But even in the best-case scenario, fine gold in pan, weighty concentrate, clustered samples, there's a hard truth. Field results can lie. Some of the most convincing pan colors come from pyrite, mica, or dyed minerals. That's why the next test isn't visual. It's chemical, and it starts with a wipe, a flame, or a splash. Even with clean samples and promising pans, gold isn't confirmed until it withstands a gauntlet of discrimination tests. The next step, sifting for signals, isn't about volume. It's about separating deception from density. Many fine-grained materials mimic gold's color or behavior, and even experienced eyes can be misled in the field. This is where physical and chemical behavior steps in to deliver clarity. Once the -40 mesh concentrate has been collected, dry it fully if not already. Use a neodymium magnet, preferably shielded in a plastic bag or casing, to extract magnetic minerals. This not only isolates magnetite and ilmenite, but reduces visual clutter in your test batch. Weigh the magnetic fraction if possible. Over 10% by volume suggests proximity to mafic or ultramafic lithologies, which may carry sulfide-hosted gold. With the magnetic component removed, inspect the non-magnetic finds under good light. A handheld loupe or digital microscope reveals shape, luster, and grain boundaries. True gold particles are rounded or flattened, with a buttery, dense glow that does not flash or flake. Suspects include pyrite, brassy, cubic, brittle, mica, sheet-like, flaky, and chalcopyrite, color-shifting, lower density. At this point, apply a simple physical test, the rub test. Take a fine suspect particle and smear it against unglazed porcelain or hard white rock. Gold will leave a metallic yellow streak. Pyrite typically leaves black or greenish black, and mica leaves no mark at all. This test is especially useful for particles too small to manipulate by hand. Scoop a cluster, smear, and interpret the residue. Then move to water behavior. Place a few grains in a small vial of clean water. True gold sinks instantly and resists turbulence. Mica and organic materials float or drift slowly. Some false positives will hover or suspend, signs of low specific gravity or inconsistent grain structure. A digital scale and graduated cylinder can offer a rudimentary specific gravity estimate. Gold averages 19.3 g/cm superscript 3, but even field tests that reveal greater than 15 suggest a high-density candidate worth keeping. For stubborn samples, it's time for acid. A weak nitric acid solution, 10 to 15%. Applied with a dropper dissolves pyrite, chalcopyrite, and iron oxides within seconds to minutes. Gold, inert in nitric, will remain unchanged, dense, bright, and unmoved. Always conduct this test outdoors with gloves and goggles. The effervescence and smell can be sharp. After acid exposure, rinse with distilled water and reassess under magnification. Finally, for completeness, introduce the heat test on select particles. Using a butane torch or focused alcohol flame, heat the suspect material on a metal spoon or ceramic tile. Gold will retain its structure and luster, while mica may darken and pyrite will decompose or spall, sometimes emitting sulfurous odor. This is a destructive test, so reserve it for samples that can be sacrificed or that give ambiguous results in prior steps. If a particle passes all of these, visual, streak, water behavior, acid resistance, heat stability, it is almost certainly native gold. Yet even these steps don't reveal the whole picture. Some of the richest insect mound samples yield no visible gold at all, because the gold isn't free, it's embedded. That's where chemical matrices like sulfides, clays, or arsenic-rich gangue carry microscopic particles invisible to any field test. And in one recent field case, that invisible gold outperformed every visual sample in value. Because it wasn't the color that mattered, but the chemistry. So how do you detect gold that hides even from the most careful eye? After the acid test clears away the obvious pretenders, what remains can still hold surprises, especially if the concentrate behaves oddly under a magnet. In insect mound sampling, one of the most counterintuitive moments comes when a gold-free looking sample resists cleanup, yet refuses to separate cleanly during the magnetic pass. You remove the magnetite and ilmenite, but the residue is still inexplicably heavy. No bright gold shows, no smear test passes, yet something dense is clinging to the fines. That's a signal worth decoding. This scenario often marks the presence of ultrafine gold locked within iron sulfides or arsenopyrite. Compounds not fully removed by weak acid and not magnetic enough for standard separation. These minerals tend to be granular, dark gray to nearly black, and exhibit a dull metallic sheen. Visually unremarkable, they carry gold invisibly in submicron inclusions or along grain boundaries. In a field context, their persistence shows up as an unexpectedly heavy pan corner that feels denser than it looks. To probe further, rerun the magnet sweep slowly and at close range. Use a rare earth magnet enclosed in a plastic bag, held just above the fines. True non-magnetic sulfides won't lift, but weakly magnetic components like pyrrhotite may twitch or shift slightly. Note any motion. If the fines are sluggish to move, but clearly resist lift, you're dealing with mixed mineralogy that might carry values inside rather than on the surface. A second layer of indication comes from water pan behavior. These sulfide-rich fines form tight tailings that settle quickly, but smear poorly. They tend to clump under the water surface tension and can show rainbow sheens or small bubbles when agitated, signs of volatile or reactive content. While not diagnostic of gold, this behavior flags the need for lab-based multi-element analysis, especially when found consistently across mounds in a pattern. In practice, many large discoveries have begun here, not with visible gold, but with weight anomalies and magnetic leftovers. A well-documented example comes from Ghana, where termite mound sampling returned no visible gold, but repeated magnetic sweeps left behind fine concentrates that consistently weighed heavier than expected. Later assays confirmed the presence of refractory gold encapsulated in arsenopyrite, averaging 0.7 grams per ton, more than enough to trigger detailed follow-up and eventual trenching. In your field kit, it's wise to carry small labeled vials specifically for these resistant residues. Keep them separate from visible gold samples and record their behavior in the field log. Magnet sweep response, water pan settling, weight feel, and acid resistance. These notes become invaluable when sending samples for multi-element ICP-MS, where detection limits drop below what any field test can capture. But there's a catch. Not all heavy residues mean gold. Some are merely manganese oxides, lead sulfides, or clay-rich fines with low commercial value. So before betting on every heavy speck, you need to understand what patterns these residues form in space. Do they cluster? Do they align? Are they repeatable? That's where technique and record-keeping separate the guessers from the finders. And when a suspicious sample performs oddly under magnet and pan, but doesn't show any gold, yet lines up with 3 others along a straight vector, it's time to change tactics. You're not looking for a nugget anymore. You're looking for a structure. There's a moment in every serious sampling session where visual tests and magnet sweeps aren't enough, where a sample resists classification, yet still feels like it holds something more. That's when the field pros reach for 2 pocket tools that, together, expose imposters and confirm survivors. Acid and flame. These are not high-tech lab procedures, but compact, rough-and-ready eliminators. Precise enough to avoid wasting time, strong enough to avoid being fooled. Start with the acid test. For field use, a 10 to 15% nitric acid solution in a small dropper bottle is sufficient. Use a porcelain spot plate or a non-reactive rock surface to test. Isolate a suspect grain or a pinhead of concentrate. Then apply 1 drop of acid. Pyrite will hiss and darken, releasing a sulfurous smell. Chalcopyrite will fizz slightly and turn green-black. Iron-stained quartz or limonite will leach orange or brown. But native gold will not react. No bubble, no shift, no color bleed. It stays bright and inert. Be cautious. Acid tests are destructive. Apply only to the least promising visible grains, unless you've got duplicates or multiple lookalikes in the batch. Always wear gloves, avoid skin contact, and never mix acids with other reagents in the field. Then comes fire, the fastest way to eliminate mica, validate luster, and test stability. Use a butane microtorch or alcohol flame, focusing on a small sample pressed into a steel spoon or fired brick. Real gold does not oxidize or discolor. Under direct flame, it remains bright and cohesive, occasionally even melting into a small bead if the particle is large enough. By contrast, mica will shrivel or delaminate, pyrite will spark and break down, and many false positive oxides will darken or explode into dust. The fire test is especially useful when acid results are ambiguous. Some dense sulfides resist weak acid, and some treated materials, such as dyed quartz, can fake luster but won't survive direct flame. Keep your flame test materials separate from concentrate containers. Contamination from burnt organics or melted sulfides can ruin the integrity of your next assay batch. But here's where it gets interesting. Sometimes a sample passes both tests, acid and fire, but still doesn't look like classic gold. It's dark, flattened, or irregular. This is where early-stage fieldwork meets its limit. The particle may be ultra-fine native gold coated in manganese oxides, or it could be electrum, a natural gold-silver alloy, with lower reflectivity. These edge cases are why consistent field recording and follow-up are critical. Even if a sample doesn't sparkle like textbook gold, if it survives every eliminator and aligns with other positives in the grid, it belongs in the send to lab pile. A key reminder: pocket tests are meant to reject false positives, not confirm or grades. They help decide what merits real investment in time, transport, and analytical cost. And they save you from loading your gear with iron pyrite glitter that looks impressive but sells for nothing. Still, some imposters play harder to catch. One, in particular, has fooled generations of panners and geochem samplers alike. It floats like gold, it shines like gold, it even clusters like gold, but it isn't. And unless you know the smear, streak, and burn behavior cold, you could chase it for weeks with nothing to show. Even after sieving, panning, acid testing, and torching, one group of imposters remains stubbornly convincing. The most notorious is mica, specifically muscovite or biotite flakes that catch sunlight with a mesmerizing glint. But there are others: fine-grained pyrite, yellow-stained quartz, even certain iron oxides that produce the telltale shimmer that screams gold to the inexperienced. They mimic gold's luster, sometimes even its weight, and they're everywhere, especially in dry, iron-rich terrains where insect mounds are common. If you don't learn to spot them early, they will waste your time, your assays, and potentially your claims. The trap begins with movement. Mica floats like it means something. In water, it swirls slowly, clinging to the pan's edge. It shines under angled sun and leaves a stubborn impression when concentrated in the pan corner. But it's deceptive. A simple test with a fingertip or a toothpick reveals the truth. Mica is feather-light, easily scattered, and will ride surface tension long after gold has sunk. Even if it appears to settle, a second rinse will lift it again. Pyrite, meanwhile, feels dense and looks sharp, especially in its well-formed cubic or granular versions. In dry concentrate, it holds its own under magnet pass, often resists weak acid for a few seconds, and retains a brass-yellow hue even when crushed. The critical difference lies in fragility. Strike pyrite with a steel nail or quartz pebble. It shatters into sharp fragments or darkens on impact. Gold deforms. It flattens. Even in micro-sized grains, gold's ductility is unmistakable under pressure. Pyrite, like glass, cannot fake that trait. Yellow-stained quartz or iron-streaked clays form the third category of deception. These materials don't shine, but they glow, a muted amber that suggests internal richness. They often show up in ant mounds where iron leaching is active, and they cling to sulfide-rich finds. But their color is usually a surface coating from limonite or goethite. A quick scratch with a steel probe or acid drop reveals pale quartz or clay beneath. No density, no smear, no recovery. To avoid falling for these traps in the field, apply a sequential method. Pan performance. Does it sink like a stone or ride the ripple? Smear or streak. Rub between quartz plates or on unglazed tile. Gold will streak yellow, imposters won't. Crush behavior. Tap gently with a hammer or rock. Gold flattens, pyrite and mica fracture. Torch test. Hold flame directly. Gold survives, mica curls, pyrite burns. Repeatability. Does the same material appear in multiple mound samples on trend, or is it a one-off shimmer? One additional test, while not conclusive on its own, adds context. A simple float test. Place a few grains in a shallow vial of water. Gently swirl. Gold grains, especially fine ones, drop instantly, cling to the bottom, and resist movement. Mica will levitate, sometimes indefinitely. Pyrite dances, drifts, and suspends, but doesn't slam down like gold does. This settling signature becomes second nature with repetition. And yet, even when all signs say no, some samples hide a different truth. A known gold-bearing mound may produce zero visible gold, pass all pocket tests, and still yield a high assay value. This is where the logic flips, and where the real lesson begins. Not all gold is visible, and not all valuable samples shine. Because in one notorious case, a barren-looking concentrate outperformed glittering ones in assay. Because the gold wasn't free. It was embedded, invisible, and everywhere. It looked like a dud. The mound showed no glint, no weight anomaly, no pyrite cluster. Just dry, gray fines barely worth bagging. But it fell on the grid line, 20 meters from two high visual samples, so it was collected anyway. Labeled sieved, magnet passed, and panned, it returned nothing worth keeping. Not a single fleck survived the wash. Most prospectors would have moved on. But when the assay results came back 2 weeks later, this blank sample posted the highest gold content on the transect. 1.4 grams per ton, more than double the best-looking mound. The gold, it turned out, was refractory, locked in arsenopyrite and ultra-fine sulfide particles invisible to the naked eye. None of the standard field tests revealed it. Only the ICP-MS and fire assay cracked the code. This one sample reframed the entire field logic. It wasn't the visible gold that mattered in the zone. It was the invisible, chemically bonded kind. And suddenly, every dark, heavy residue that had been passed over took on new significance. This reversal isn't just anecdotal. It's a known pattern in terrains dominated by fine disseminated mineralization, especially in greenstone belts, hydrothermal alteration zones, or deep residual profiles. Insect mounds in these areas tap into oxidized caps or weathered sulfide horizons, where gold is no longer free and particulate, but absorbed onto iron oxides or embedded in secondary minerals. In the Ghana case that mirrors this, termite mounds across a lateritic plain yielded only minor visible gold. But when bulk samples were run through aqua regia digestion and analyzed with ICP, several returned gold values above 1 gram per ton. The gold was present not as flakes, but as ionic inclusions within ferruginous clays and arsenic-rich fines, undetectable with pan, magnet, or acid. This realization transforms the field approach. Instead of privileging only glittering samples, you now also prioritize dark fines with high sulfide smell, sticky texture, or unusually high water retention. These qualities often point to mineral matrices that hold sub-micron gold. Even more, they help define metallurgical character. indicating whether the deposit, if confirmed, would require free milling or refractory processing. To test this in the field, one add-on method becomes invaluable: roasting. A small pinch of dark concentrate can be heated gently in a crucible or steel dish until color change occurs. Arsenopyrite will release a garlic odor. Arsenic gas, take extreme care, while pyrite shifts from brassy yellow to red-brown hematite. Post-roast material can be panned again. Sometimes, heating liberates enough gold to see in the concentrate. It's not foolproof, but it can offer a directional clue. This shift, from visible gold to chemically bound gold, requires reframing what a positive sample looks like. It emphasizes pattern over glimmer, and it means that some of your most important clues will come not from what you can see, but from where and how often the same behavior recurs across mounds. When the visual fails, repeatability speaks louder. If 5 dark, dull mounds in a row show similar mass behavior, texture, and response, but no gold in pan, it might be time to trust the pattern, not the sparkle. But to scale this insight and avoid the trap of overinterpreting flukes, you'll need a framework, a proven, structured method recognized beyond individual success stories. Something tested, repeatable, and scalable. Insect mound sampling isn't a fringe trick. It's a field-proven technique backed by decades of applied research and commercial success, particularly in terrains where traditional geochemistry underperforms. What began as anecdotal observation has matured into a geochemical reconnaissance strategy used by majors and juniors alike. The method's validation comes not from lab theory, but from direct correlations between mound content and subsurface mineralization, repeated, mapped, and monetized. The strongest validation comes from West Africa's greenstone belts, where termite mounds routinely rise over lateritic plains with little surface expression. Geological surveys across Burkina Faso, Mali, and Ghana have shown consistent geochemical anomalies in termite mound soils that align with hidden gold systems. In multiple documented projects, termites unknowingly tapped into bedrock mineralization up to 15 meters deep, far beyond the reach of shallow soil samples. Mound material was collected, sieved, and analyzed for multi-element anomalies, and gold was just the start. Arsenic, bismuth, antimony, and tungsten also showed up, classic pathfinder elements that signal hydrothermal activity. One study published by the British Geological Survey involved over 300 termite mounds sampled across a flat, iron-rich plateau in southeastern Burkina Faso. None of the mounds showed visible gold, but statistical analysis of the sieved, dried finds revealed 2 corridors of arsenic and gold co-enrichment. These corridors matched magnetic lineaments picked up in aerial geophysics and later intersected bedrock-hosted gold veins in RC drilling. The termite data didn't just hint, it predicted. In Australia, the story repeats with ants. In the Northern Territory and parts of Western Australia, harvester ant mounds in regolith-covered zones have been used to detect geochemical halos overlying blind deposits. In one case, a soil survey failed to detect gold over a dolerite-hosted shear zone due to transported cover. But ant mounds, small, consistent, and low-profile, returned subtle but consistent gold and copper anomalies. When mapped, the anomalies formed a northeast trend that precisely overlapped the hidden structure confirmed by follow-up drilling. The power of insect mounds lies in their vertical integration. Termites and ants access material from multiple depths, mix it during construction, and stabilize it in situ. The mound becomes a natural core sample, chemically representative, undisturbed, and physically concentrated. And unlike traditional soil pits, these samples don't require permits, machinery, or vegetation clearing. A scoop, a sieve, and a GPS are enough. But there are rules. To achieve valid comparisons, sampling protocols must be consistent. Same mound type, same depth of collection, same sieve mesh, same drying time. Without that, the data skews. That's why industry and academic institutions, like CSIRO in Australia or geochemical labs in Bamako, have developed field manuals specifically for insect mound sampling. These outline protocols for bagging, drying, sieving, and analyzing mound soils to produce reliable, repeatable results. The method scales, too. Junior explorers use it for early-stage reconnaissance. Major operations use it to refine drill targeting in regolith-covered belts. Some operations even build databases of mound geochemistry over years, layering them with geophysical data to form high-resolution subsurface models. This validation across continents, deposit types, and operational scales anchors the technique as more than folklore. It's now a respected, if still underused, part of the exploration toolbox. But like any method, it has its blind spots. It works best in specific terrains, those with insect stability, shallow weathered profiles, and undisturbed soil cover. So where exactly does this method shine? And where does it fall flat? That's the next filter you'll need to apply before sampling a single mound. Not all terrains are equal when it comes to insect-driven sampling. While ant and termite mound geochemistry has proven effective in multiple gold-rich regions, its utility depends heavily on soil type, climate stability, depth to bedrock, and most critically, the behavior of the insects themselves. If the biology or geology fails the conditions test, the signal can be lost or worse misread. The method thrives in stable, well-developed regolith. This includes tropical laterites, arid peneplains, and weathered greenstone belts. Terrains where mechanical soil disturbance is minimal and insect colonies persist undisturbed for years. In these settings, mound-building species like macroterms in Africa or iridomyrmex in Australia construct enduring structures using material from up to 15 meters deep. This vertical sampling reaches into transitional zones and even saprolite, pulling up material with strong geochemical signatures that traditional topsoil surveys would miss entirely. Ideal conditions include arid to semi-arid climates, where erosion is slow and mounds remain intact for decades. Residual soil profiles, especially those derived from ultramafic, mafic, or greenstone lithologies. Flat to gently undulating terrain, where overland flow is minimal and mound chemistry isn't diluted by runoff. Well-established insect populations, which occur in undisturbed land far from heavy agriculture or construction. In these zones, termite and ant mounds provide a geochemical cross-section of subsoil materials, offering clues about blind mineralization that lies under transported cover or thick weathering profiles. When sampled properly, they can predict the presence of gold veins, shear-hosted systems, or even disseminated ore bodies without a single drill hole. However, the method begins to fail in saturated or mobile soil conditions. In flood-prone zones, deltaic plains, or areas with high seasonal erosion, mounds are often young, shallow, or contaminated. The insects here don't dig deep. They follow moisture or root paths, not geological structures. Likewise, in reclaimed land, plowed farmland, or recent mine sites, any mound sampling becomes geochemically meaningless. The topsoil is already mixed, and any subsoil trace is likely to be either absent or masked. Other red flags: clay-rich vertisols. These expand and contract seasonally, disrupting mound stability and smearing signals. Alluvial basins with transported overburden. Insect mounds here may tap sediment layers rather than mineralized bedrock. Cold or high-altitude zones. Ants and termites are often absent or inactive in these environments. Disturbed anthropogenic zones. Construction, vehicle traffic, or even intensive grazing can fragment colonies and corrupt sampling. Understanding insect species is equally important. Not all mound builders excavate deeply enough to matter. Many common species only rework topsoil and bring no fresh geochemical data. Field identification guides can help, But a simple rule is mound persistence. If it has withstood multiple seasons and appears hardened or cemented, it likely has depth sourcing. If it crumbles easily and has fresh, loose sides, it's probably too shallow for meaningful analysis. In short, if your terrain supports mature, undisturbed mounds over regolith that hasn't been turned, scraped, or saturated, you're likely in a viable sampling zone. But recognizing those preconditions early prevents wasted effort and false hope. Next, we narrow the target even further. Not by terrain, but by mineral association. Because while mounds point toward gold, the company it keeps, quartz float, iron staining, and specific pathfinders, can sharpen your aim before the first assay. Gold doesn't travel alone. Even when insect mounds are your primary sampling tool, recognizing what surrounds them, visually, chemically, and structurally, can mean the difference between chasing a scattershot anomaly and locking onto a true mineralized system. Insect mound data is most powerful when integrated with known geological indicators. Quartz float, Gaussian staining, and pathfinder elements like arsenic, bismuth, and antimony. These features, when seen in proximity to gold-positive mound samples, create a multi-signal convergence that boosts confidence and justifies follow-up work. Start with float materials. Quartz float, loose quartz fragments on the surface, is a classic early sign of underlying hydrothermal activity. But not all quartz is equal. Milky, featureless quartz is common and often barren. What you want to spot are pieces with iron staining, visible vein textures, or brecciated edges that suggest proximity to fault-controlled mineralization. If ant or termite mounds are clustered near these fragments, and especially if some specks of sulfide-rich rock are mixed in, take notice. Next, look for Gaussians, oxidized caps formed when sulfide-rich rocks weather at or near the surface. These appear as rust-colored zones, often mistaken for ironstone. A Gaussian near or beneath mounds showing subtle gold or arsenic response is a strong indicator that you're sitting above a sulfide-hosted gold system, even without visible gold. These structures may conceal massive or disseminated sulfides beneath the oxidation line. Now, consider pathfinder elements. Arsenic is the most consistent companion to gold in a range of deposit types, especially orogenic and Carlin-style systems. Termite mound samples that return elevated arsenic, even without visible gold, deserve attention. Bismuth, antimony, tungsten, and mercury can also co-occur with gold, and their presence helps resolve ambiguous results. For instance, a sample that tests low in visible gold but high in arsenic and antimony suggests a deeper or refractory system worth chasing. Many mobile XRF units can now detect these elements in the field, offering real-time multi-element geochemistry. While not a substitute for lab assays, XRF readings taken across a grid of mound samples can reveal element halos or enrichments that correlate with subsurface structures. Overlay these anomalies on your GPS plot, and patterns often emerge that would otherwise remain invisible. Also, study vegetation patterns. In some regions, hyperaccumulator plants concentrate metals in their tissues. Stunted growth, yellowing leaves, or bare patches in an otherwise uniform landscape can signal mineral stress zones. If such anomalies align with mound clusters or float trends, you're seeing a convergence that's more than coincidence. But integration isn't just about adding data. It's about adjusting thresholds. A mound that tests just above background in gold might be dismissed, until you see it's part of a line that tracks a quartz flow trend and shows consistent arsenic enrichment. That combination turns a maybe into a map it, sample it, follow it. Ultimately, integrating indicators is about building a field model. What does a promising anomaly look like here, in this terrain? Once you establish the local pattern, you can apply it across other targets in the same belt, multiplying your efficiency. But to trust the data you're collecting, whether visual, chemical, or structural, you need a consistent, repeatable field workflow. Because it's not just what you find that matters. It's how you found it, and whether you can repeat that result again and again.